Okay, so continuing where we left off, we're using Snell's law here in the context of this figure, and we have four quantities. Three of them are known. One of them is unknown. That would be the angle theta 2. So we solve for theta 2, or more specifically, we solve for the sine of theta 2. And we find that sine of theta 2, we take the two indices of refraction. We can look them up. Air is approximately 1. It's slightly bigger than 1, but to three significant figures, it's 1.00. Water, fresh water, is 1.333. Theta 1 was 40 degrees, so we do that calculation. Sine of theta 2 is 0.4822. So there is an angle now that we didn't know that we do know. Okay, so what we can do is to solve for this quantity x2. Okay, so what's x2? It's the distance of from this point on the bottom of the water to the keys, and this point is directly below the point where the beam of light from the flashlight enters into the water. So you can think of this as a right angle triangle that I'm tracing out here. Okay, the vertical is one side, x2 is the other side, and this pink line here, where the ray of light moves along in the water, that's the hypotenuse. So if you think about it, do the trigonometry, x2 is the side of the triangle opposite to the angle theta 2. So you could say that sine of theta 2 is x2, this quantity, divided by the hypotenuse. The hypotenuse, well, we can calculate that using the Pythagorean theorem. So that'll be the square root of x2 squared plus 1.6 meters squared. And what do we know about this quantity? Oh yeah, sine theta 2, we just calculated that. That was 0.4822. So what this equation gives us is one equation and one unknown. So all you have to do is to solve that equation, one equation for the one unknown, and you have it. Okay? So what you can do is just don't worry about the sine of theta 2 anymore. We have this ratio is equal to 0.4822. Multiply in this equation, multiply both sides by the denominator. That's the square root of the sum of the two squares here. And then take the square of each side of the equation. So this is math that should be familiar to you from high school, right? Solving one equation, one unknown. Multiply by the denominator to get rid of this fraction, and then square both sides to get rid of the square root. And you end up with a quadratic equation. This is the equation you end up with. x2 squared is equal to what we had originally on the right-hand side, 0.4822 squared, multiplied by the square of the denominator. That's just the same as the denominator without the square root. Multiply through, and then you can continue solving this equation. What you can do is take this term to the left-hand side of the equation, factor out x2 squared. So you have x2 squared minus 0.2325 x2 squared, or 1 minus 0.2325, all multiplied by x2 squared, is equal to 0.5953. So you can solve that equation and you get x2 is 0.881 meters. Okay, so we're getting there. What we want to know is what is the distance of the keys horizontally on the bottom, on the lake bed, bottom of the water, from the point directly below the edge of the deck. And we said what we're going to do is calculate x1, calculate x2, add them together, and that'll give us x. Well, we've got x2. Now we have to do x1. So how are we going to calculate x1? Well, this shouldn't be too difficult. Okay. You note that, let's see, we have, once again, we have a right angle triangle. Okay, I'll have to go back to this figure here. The right angle triangle will be this one, okay, that I'm tracing out. So this side of the right angle triangle is x1. This side is 0.50. This pink line, which is the line the light travels on in the air before it hits the water, that's the hypotenuse. Okay, so once again, you could say that the sine of this angle theta 1, which is 40 degrees, is equal to x1, this side of the triangle, right, which is the same as this. This side of the triangle, x1, divided by the hypotenuse. And once again, we'll use the Pythagorean theorem to calculate the hypotenuse. So it'll be the square root of the sum of the square of x1 and the square of 0.5 meters. And we can solve for x1 in the same way that we solve for x2 in the equation above, right? You multiply by the denominator, square both sides, isolate the unknown x1, and just like we did for x2, and you'll discover that if you do that, you get 0.420 meters to 3 significant figures. And x2 plus x1 is 1.3 meters. That's the distance that the keys are from the edge of the dock on the bottom of the water. So there we have it. We've used Snell's law and a little bit of trigonometry to solve this problem. Okay, moving along. Let's talk about something called total internal reflection. So let's imagine we go from one medium to another. So we're shining light from one medium to another medium. Maybe the first medium number 1 is glass, and the second medium number 2, could be air or something like that. And what happens to the light as it crosses this interface? Well, the light bends. Now remember, we said when light went from a lower index of refraction to a higher index of refraction, it bent towards the normal. Here it goes the opposite way. Okay, so the light is coming, let's say, along ray number 1, hits the interface. We're going from glass to air. The index of refraction is going to decrease across that interface. So the light will bend away from the normal. Remember, the normal is this line which is perpendicular to the interface, perpendicular to the surface. Okay? And we can use Snell's law to determine the relationship between the angle of incidence and the angle of refraction. Okay, we know how to do that. Now what happens is, as this direction of this light becomes more, well, at an angle which is increases relative to the normal, okay? So the light is becoming more and more slanted relative to the normal. What we find is this refracted ray will tend to bend more as well. But then there will be some angle that we call the critical angle, where the refracted ray of light will just skim the surface of the interface. It won't actually, the light won't actually go out into the second medium, but it will just skim the surface here. And if we increase the angle of incidence even more, so we consider ray number 4, this time nothing goes from glass into air. Okay, all of the light gets reflected because that reflection is total and it's internal to the first medium. We call it total internal reflection. So how do we calculate this so-called critical angle? Critical angle where if you go past that angle, you get no refraction, and it's all reflection. Well, the way we calculate it is we go back to Snell's law. So here's Snell's law. And we're going from medium 1, and the angle of incidence is, we'll call it theta sub c. C is for critical. And medium 2 is n2 times the sine of, okay, if the refracted ray just skims the surface here, that means this direction is perpendicular to the normal in medium number 2. If it's perpendicular to the normal, it means the angle is 90 degrees. The sine of 90 degrees is 1. So that means the sine of the critical angle is simply, if I divide each side by n1, the sine of the critical angle is the ratio of n2 divided by n1. So there we have it. And we note that this only works if N2 is less than N1, because of course, the sign can't be greater than 1, so N2 has to be less than N1. Okay, so let's look through an example here. Let's say we have a glass prism. Okay, so it's just a triangular piece of glass. And the light is shone into this triangular piece of glass. Here it goes. And it strikes the surface. And when the glass is surrounded by air, we will get, as it turns out, total internal reflection. Okay, we get total internal reflection. But we want to know what would happen if we did this same thing. The light went into the glass, struck this internal surface. What would happen if, instead of there being air on the other side, the prism is immersed in water, so there would be water on the other side? Okay, so what we need to do is, what we're going to do is to calculate the critical angle for the glass-water interface. So this is really easy. We have our equation. The sine of theta sub c is the ratio of the two indices of refraction. And so medium number 2, that's outside over here, that's water. Medium number 1, that's inside, that's glass. So you look up these numbers. Water is 1.333. Glass, remember there is a range of values for glass. We'll say that, well, I guess we're given this, this information for this particular glass. The index of refraction is 1.5. So we calculate that ratio, and we have this sine of theta sub c is equal to 0.889. Okay, take the inverse sine of that, and we get 62.7 degrees. And the question is, what can we expect? We've calculated this critical angle. If we repeat this experiment, this demonstration, whatever you want to call it, what are we going to see in the case where we have water surrounding the prism and not air? Okay, so the first thing to note is, in this case here, so forget about the first interface, the light is coming in perpendicular, it's coming in perpendicular to this interface. Snell's law, it turns out, will tell you that it will keep going in the same direction. Okay, so you might want to prove that to yourself, but it turns out to be the case. Here's where you could get possible refraction and or reflection. But what I want you to see here is this prism has a, let's see, what am I trying to say? The angles of this prism here are both 45 degrees. So you see the length of this side of the triangle is equal to the length of this side of the triangle. And so that means this angle is 45, this angle is 45. So if you draw, and I haven't drawn a line here, but imagine you draw a line from this point, let's say to the corner of the prism, that would be perpendicular to the surface, so that would be the normal. Here's the surface, here's the normal, okay? If you do the geometry, what you'll discover is the angle between this line, which I'm trying to trace out here, the normal to the surface, and this line, which is the incident ray, will be 45 degrees. Okay, so this is the angle of incidence, is 45 degrees. And we have just calculated, however, that the critical angle is 62.7 degrees. Okay, so because the angle of incidence is less than the critical angle, remember how that was defined, the critical angle, your conclusion is the light will not be totally reflected at the interface. Okay, if the angle of incidence, and again that's the angle between this line and this line, if it were greater than the critical angle, then you would get total internal reflection, but that's not what we have here.